Hello AP Stat students, back with the first lesson of the chi-square unit. That CHI again is chi, not chai or chi. And this is the first lesson, which is goodness of fit, which is a certain type of chi-square test. First and foremost, to identify what makes this test different from, say, the means or the proportion test, is this test deals with categorical variables. Or this unit, I should say, deals with categorical variables. Okay, so it's not the mean number of anything. It's not the proportion of people who agree with something. This has to do with grouping into different groups that are categorical variables. So it might be based on race or ethnicity, religion, grade, things like that. So there's going to be a different format that you'll see here in this particular lesson. So when do we use this is the first thing we need to know. And again, that's going to be, you'll see things like tables of information that look a little different versus the list of numbers or the list of yeses and nos or something we might have seen in the past. The data characteristics, again, comes back to the categorical. How might it look in our own research or project work? If you can break down projects into, say, if it's customer reviews, what has a positive tone versus a neutral tone versus a negative tone? Those would be categorical variables, and we'd list, how many fit into each one of those. And then eventually we'll talk about what makes it different than the other type of chi-square test. So here's an example. A company sells 4 sizes of shirt: small, medium, large, and extra large. This is what they expect to have happen. 20% of the customers will need a small, 30% medium, and so on. So this is going to determine their inventory right here. But then over the last month, they have this breakdown of actual sales. And so what they might want to do now is look at how close did they hit their inventory numbers. And if they miss by a little bit, again, you expect to miss by a little bit. That's just natural variability that occurs from sample to sample. So what we're really looking for is, did these significantly miss their estimations? And by significantly, again, we're talking statistically significantly, which is what we'll look into now. So to start off here, what are our hypotheses? So unlike these past units where it's been mu equals a number or p equals a decimal, this is now complete sentences in our hypotheses. So essentially here, in this particular example, what we're trying to find evidence for is basically, did we sell t-shirts in a different ratio than we expected to sell? So for this example, your null hypothesis would be the observed number of shirt sizes that we sold equaled the expected number based on our previous belief of sizes. Again, there's a number of ways you can word this. This is pretty poorly worded by me, but what we're essentially saying is, did we hit, and again, I can put this in a different color here, did we hit our ratio or not, is really what we're checking. And so the alternative hypothesis in this particular problem would be essentially that the observed number of shirt sizes and so on is different or did not equal the expected ratio. And again, don't cut it off on a test answer or anything like that in terms of your hypotheses, but you'll see it do that a fair amount in our examples, just so you don't have to watch me write the whole time. But again, so what we're trying to find evidence for is basically, is the observed distribution not equal, is the observed distribution not equal to the expected distribution? So the null hypothesis, of course, is, did the observed hit the expected? And again, the expected could be equal sizes. It could be a different ratio of, equal number of small, medium, large. Could be some different ratio of small, medium, large. But in this particular problem, The ratio that they have is what they have sold T-shirts in the past, and so they're checking on that. So just be mindful of that. If it's say Starburst flavors, and we expect to get if we have 100 Starbursts, we expect them to be equally distributed. Then we would expect to just divide the 100 into the 4 main, red, orange, yellow, and pink flavors, and we'd have 25 of the expected. So we'll look at how we get the expected in this particular one as we move forward. So when we run this, similar to what we've done in the past, we need to verify that our data can be trusted. And being trusted, again, has to do with the conditions. So let's talk about the conditions. And first of all, the type of test here, this is a chi-square goodness of fit. So this right here, what looks like almost an italicized X, is chi. It's a letter. And then square, of course, is the superscript 2 right there. So chi-square goodness of fit. In this unit, because we use the same formula throughout the unit, it actually is probably a little easier to use the formula, which we'll get to here shortly, what that formula looks like, that you can just write the formula each time to identify the test. But for right now, getting into the conditions, the first condition, not surprisingly, is simple random sample. And simple random sample, again, what we'd expect it to be able to do is to be able to quote the question. I'm not going to go back to it right now, but if this were a random sample of T-shirts that we sold over the last month, then we'd have that. Now, of course, with something like that, we probably have all the T-shirts in some sort of database, selling database that we have, and so we wouldn't necessarily take a sample. But typically, your SRS is going to be to quote the question. Now, the second condition is actually the same as the proportion unit, which is large enough sample. Okay, it is not in this unit normality. And we'll get into that a little more later when we talk about what the chi-square curve looks like. But we do not want to mention the word normal in the chi-square unit. So just a heads up on that. Large enough sample in this particular problem is actually, can we verify that all of the expected counts are greater than or equal to 5? So how we get these expected counts is where we have to do a little bit of work here. So I'm actually going to zoom in up here so that we can fit this in, just to show how we get these expected counts. So back on the original page with the data, it gave us 4 different sizes of shirts: small, medium, large, and extra large. And it said that it observed we had sold 227 smalls, 319 mediums, 388 larges, and 66 extra larges, which means the total number of shirts that we had sold over the last month, we can go to our calculator, add this up by hand, was 1,000 shirts exactly. That means that our expected counts have to also add up to 1,000. These two numbers right here have to be equal, because we can't say that we sold 1,000 shirts and now we're going to compare it to a ratio that's based off of 5,000 sold, because then we know our observed values aren't going to match the expected, even though we're still considering percents ultimately. So what we want to do then is say, okay, we expected 20% of the shirts to be smalls, which means out of the 1,000 sold, we expected 200 of them to be smalls. And again, that's because 200 out of 1,000 is 20%. We expected 30% to be mediums, which means we expected 300 of them to be mediums. We expected 40% to be larges, so 400 to be larges, and we expected 10% to be XLs, so we actually expected 100 to be extra large. So what you can see here is we oversold the smalls by about 27 shirts, and the mediums by 19 shirts, and the larges we undersold by 12 shirts, and the extra larges we undersold by 34 shirts, which of course the extra larges kind of stand out here, not just as the biggest miss, but they're also the biggest miss with the smallest sample sizes. And so a big miss with a smaller sample size means a lot more. For instance, if we expected 100 and sold 200, is a lot different than if we expected 1,000 and sold 1,100, where we, again, both of them have a difference of 100, but to be double versus just 10% more is a much different ratio. So keep that extra large in mind, because that's a pretty notable difference right there in those numbers. So as we move forward here into this actual table here, this was again what we were just doing. We expected to have 200 here and 300 here and 400 here and 100 here. So you don't always have to draw the table, but the reason the table is important is really just because of this column. And I didn't fill it in on the conditions on the last slide, but this column we would list in our conditions and note that these are the expected values, expected counts, and these are all greater than or equal to 5. So that's verifying the second condition. So that is something that is valuable for verifying that condition, but then also these values become the important part for calculating our test statistic, which is on to our next step. So step 3 is called the mechanics. Again, is the calculations that we have to get to our test statistic and to our p-value. But in this unit, you can see right here, this is the formula. And I'll write this formula again. Down on the bottom, it looks like this. Chi-square equals the summation, which just means you're going to add all of these up, of the observed number minus the expected number squared divided by the expected number. You may even have used this formula. It is a percent error formula or something in a science class. But what that means is the test statistic is actually going to be these 4 numbers added up here. And those 4 numbers are different iterations of this formula. So the first iteration right there would be the smalls observed minus the smalls expected all over the smalls expected. And you will not have to write out this whole formula every single time, but it's important to know where this came from. So if you calculate this, this ends up being a value of 3.645. Now, for our purposes right now, that 3.645 doesn't really, it's not number of standard deviations from the mean. It's not anything like we've seen in these last couple of units. So don't get too caught up in the specific meaning of that, because it means something a little different depending on our sample size, or number of groups is really more important. And so so be mindful of that does not mean number of standard deviations from the mean. So calculating this out, and I'll talk a little bit about how to do that on a calculator, but calculating this out shows that the second iteration has a 1.203, the third one is 0.36, and the last one is 11.56. So here's what's happening. On this particular problem, this is a chi-square goodness of fit test, and the chi-square curve looks something like this, actually. It's skewed to the right. And skewed to the right has to do with the idea that you can't get a negative number here because you're squaring this numerator, and the expecteds are always going to be a positive value. And the further the O and the E are from each other, the further down the curve you're going. So in this particular problem, what you're seeing is that this 3.645 brings us a certain distance down the curve. Then the 1.203 brings us a little further down the curve. Then the 0.36 brings us a tiny bit further down the curve. Then that 11.56 brings us way down the curve. And so what ends up happening is the p-value here is always the area to the right of what these all added up to. So in this particular problem, the chi-square value ended up being 16.77. So the value on the axis here is 16.77. And the p-value on this one, which again is the area right here, that p-value ended up being 0.0008, which means the difference that we observed between the number of sizes of each shirt that we sold and what we expected was like a tenths, hundredths, thousandths, 10,000s, 8 in 10,000 difference. In other words, if we had checked 10,000 months, we'd expect only 8 of them to have missed our mark by this much, assuming it was supposed to follow the rule that we thought, which was that 20%, 30%, 40%, 10%. So our miss here was so drastic that we ended up having some pretty strong evidence that our original expected belief was just wrong. So maybe this is our first month of selling t-shirts, and it just turned out we were bad at guessing our inventory. So as we move on, then, what we need to make sure to list is the chi-square test statistic, which I put on that last one, but I'll note again here, is 16.77. We need to mention the p-value, which, as I said, was 0.0008. The degrees of freedom is the number of groups minus 1. So in this case, there were 4 sizes. So there are 3 degrees of freedom. Again, number of groups, not number of individuals. A lot of times students will take the 1,000 t-shirts and subtract 1. It's just the 4 sizes and subtract 1. What you're basically finding is how many O minus E squareds divided by E are you going to do, and then subtract 1. Now, one other element that is good to include here, and your calculator will give this to you, is to just write the values just to a couple decimal places that you added up to get our test statistic. So our chi-square test statistic was this, which was, again, approximately equal to that. Now, again, your calculator will give that to you, and what you would need to do on your calculator is you would go to Stat, Edit, put the observed in list 1 and the expecteds in list 2. So those values you'd have to find first. Observed would be given to you. Expected you'd have to find based off the total number that we're talking and the expected ratio. Are they all even? Is it like this where it was 20, 30, 40, 10% for the extra larges and so on? After you put them into a list, it's stat, test, chi-square, GOF. Now, what you're going to have is it will ask you for your observed and your expected list, which will presumably just be list 1 and list 2. And then it will ask you for your degrees of freedom, so you need to consider that number of groups minus 1 to get that. Now, what happens is when you run the test, at the very bottom of the result, your calculator gives you something that just labels as CNTRB. CNTRB stands for contributions, and what that is giving you is all the values that contribute to our test statistics. So that's why I say it's a good idea to just write this, because your calculator gives it to you, so you're just copying it down, and it's showing a little work for your test statistic, which can help with things where you have borderline scores on the AP exam, and if you give a little more work, and they might be more apt to round up if you showed that you know where that value came from. Okay, so moving forward to the conclusion. So again, in this particular problem, we had an extremely small p-value. So we had a p-value that was about 0.0008, which of course is less than 0.05. So we would reject, since when p is low, reject HO. So we have evidence for HA. So in this particular problem, that conclusion would look something like this. Based on our evidence, p-value approximately 0.0008, less than 0.05. We reject the null hypothesis, And it's always good to write out null hypothesis, but I'll save you that here. So there is evidence. And then we just restate HA. You can literally copy what you wrote for HA at this point. But I'll say in this case, so there is evidence that we sold shirts in a different size ratio than expected. In other words, we expected to sell so many small, medium, large, and extra large, and we sold a different ratio of shirts, and so we probably should shake up our inventory breakdowns for the future. So the follow-up question you may get is this idea here: was there a particular size of shirt that was most responsible for our final decision? And this comes back to the contributions. If we reject, we want to look for big contributions. In other words, where was the observed and the expected most notably different? And if you recall, that was definitely in the XL shirts. That contributed 11.56 toward our test statistic, which wasn't much bigger than that. Our test statistic was only 16.77. So the extra larges contributed over 2/3 of it, or almost 2/3 of it. Over 2/3, almost 3/4 of it. And so the extra large is really where our size inventory issue is at. And again, the extra large actual number that it missed by wasn't much different than the other shirts. But the big issue here was that the extra large had a small expected and missed by a lot. And a small expected and missing by a lot, because you're dividing by a smaller number when you write this formula. If you're dividing by a smaller number, that test statistic is going to blow up a lot faster if your O and your E miss each other by a fair amount. So the extra large was the biggest reason we rejected. And had we been a little closer on the extra large and just missed the other sizes by a little more, we might not have had such a big test statistic in the end. So here's just a picture of the curve in the end. Again, it does change shape as the degrees of freedom change. So that's just like the T curve changes shape as the degrees of freedom change. The p-value is always area to the right. So just as you would see, just to be mindful of that, p-value is always to the right. So just a couple pictures there. This is kind of what we'd maybe say a more fully developed chi-square curve, where that skew right is a little cleaner and you see the big picture. Over on the right here, you see that it actually, with 1 degree of freedom, it starts way up high and just kind of falls down. The reason that the mode of these goes further to the right each time is, of course, because as degrees of freedom increase, that means you just had more O minus E squareds divided by E, because again, degrees of freedom is just 1 less than the number of iterations of this formula you have to run. Because if we have 10 groups, then there's 10 rounds of this formula, so there'd be 9 degrees of freedom. So that's why the high point of the curve just continuously moves to the right as the degrees of freedom increase. So you do have to be careful just if the expected values are small. Be mindful of that you may fail your second condition. But also, if your expected values are small, you're going to end up having situations where the test statistic can blow up pretty fast. Including those C and TRB values can be great. And then just make sure that it is a goodness of fit and not our next option, which is the second lesson of this unit, which uses matrices instead of lists. And so it's a fundamentally different type of problem. And sometimes students forget to catch that difference. So we'll follow up with that more in lesson 2. But thank you for listening to chi-square goodness of fit. Take care.